Okay, so we've got first video of Unit 3, bonding. And we're going to start off talking about ionic bonds. Ionic bonds, pretty general, yet at the same time, there are definitely going to be a few things that we're going to talk about newly. So in this presentation, you're actually going to get 4 different sections kind of thrown in together, ions and ionic bonds we're going to talk about. And I was kind of wondering if you might be able to determine why I chose this background, which appears to be a baton handoff or track or something. Can you come up with it? Well, of course. It's because there's a transfer of something. The baton is being transferred from one thing to another, and that's what ions do. They transfer things. Ha 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 ha. I'm so funny. All right, moving on. Okay, so bonds. Generally speaking, there are a lot of methods of study that will be used to obtain information on materials. For instance, we can take a look at physical properties of materials. We can look at if they conduct heat, if they're hard versus soft, if they have a high or low melting point. We can look at solubility. We can determine if they will mix with water, mix with oil, and then the properties of resulting solutions would be, like, is the resulting solution electrically conductive or not? Another thing to characterize materials would be behavior in electric fields. For instance, if an electric field is applied to this material, will it magnetize or will it not magnetize? And also, bond energy. What's the energy required to actually break a bond? So with all of this, you're going to see that different materials have different properties. So why do certain materials have specific properties and behaviors? Well, it all comes down to minimizing energy, that they will have this or that property as a basis of kind of keeping the whole energy of its system at an absolute minimum. That's really what that's what chemistry works on. As an overall idea, chemistry is based on stability, and low energies are more stable than high energies. So as we're talking about bonding, we begin to talk about how things combine with other things to have some of these behaviors and properties, and it's all based on minimizing energy to try to keep the system at low energy. So when we try to take a look at the type of bond that you might be forming between two different chemicals, two different atoms, it's generally the electronegativity difference that you'll take a look at. If you have a high electronegativity difference versus a low electronegativity difference between two atoms, that's really what is going to influence it. So if you would take a look in your textbook, page 354, what you're actually going to see on that page in figure 8.3 are what are called Pauling scale electronegativity values. So to go back and think about something that we talked about just a couple of presentations ago with electron affinity and electronegativity, they are very similar, but with electronegativity, you are on the Pauling scale, which is a 4 to 0 scale. So the higher the number, the better the atom is at attracting electrons to itself. So again, it's a lot like electron affinity. If you just take a look on the same page, table 8.1 on the same page, the larger difference moves from being nonpolar to polar to ionic. So what you end up doing is comparing the two atoms on the Pauling scale. So for instance, if you compare carbon at a what is it, a 3.0? I'm not looking at any values right now. Versus fluorine, I know, is a 4.0. You can see that they have an electronegativity difference. Hydrogen is a 2.1. If hydrogen bonds with fluorine, which is a 4.0, that's a very big difference in electronegativity. So these aren't perfect ranges that you're seeing on the screen. You might even notice that nonpolar covalent to polar covalent, they both are like the 0.4s in both. It's not perfect, but basically the lower the difference between the two atoms' electronegativity values, the more nonpolar it will be. And then as you begin to have a higher difference, you're going to be a polar covalent bond. And then if the difference goes above 2, or if it's close to 2, you're going to be an ionic compound. So there tends to sometimes be questions about that, but again, you're just comparing two different numbers. So if you take a look at fluorine and then compare it to sodium, if those two numbers, when you subtract them, end up being above 2, it's an ionic bond. If the two numbers are between 0.4 and 2, then it would be considered a polar covalent bond. But this is it's kind of a continuum. It's sort of a shades of gray that you aren't exactly sure whether you're white or black, but you're some shade of gray in the middle. And so it's a continuum, and it's not meant to be this perfect thing. But it just gives you an idea of which bond would be polar, nonpolar, or ionic. So for a sample exercise here, it says order the bonds according to the polarity. So you have a hydrogen-hydrogen bond, an oxygen-hydrogen, a chlorine-hydrogen, a sulfur-hydrogen, and a fluorine-hydrogen. And if you were asked to put these in order of relative polarity, my hope would be that you would understand that the hydrogen-hydrogen bond is not polar at all, because they would both have an electronegativity value of 2.1. To show the complete answer, hopefully you can kind of read it. I know it's a little bit fuzzy. But you can see how they are just looking at these two different values. So the electronegativity difference here is 0, which means it's a nonpolar covalent bond. Here, 2.5 to 2.1, you see a 0.4 difference. And then it goes all the way up to the fluorine hydrogen that we talked about, which is a 1.9, which is nearly 100% ionic. So you can put those in order just by comparing the two numbers. Okay, so a little talk here on the next few slides about energy involved in forming these ionic bonds. In fact, this will go on for, about 4 slides here. So we're going to really be focusing in on sodium chloride. When we take and we want to bond 2 atoms together, what we need to happen for this bond to really be stable is for you to create a lower energy state than when you started. So as we put together sodium and chlorine, we need to understand that the sodium and the chlorine apart would have a higher energy than when we put them together. And that's why they stay together as a stable compound, because it's a lower energy level. So if we're going to bond these two things together, it has to occur in steps. So first off, if we want to form NaCl, we would have to have the sodium lose an electron. Once the sodium loses an electron, then the chlorine is capable of gaining that same electron. Once the chlorine gains the electron, and your sodium is now positive and your chlorine is now negative, now it would be possible for those resulting ions to attract to each other magnetically, and that would form, we are assuming at this point, a lower energy overall than the sodium and the chlorine atom apart. So what we're going to do is now look a little closer at each of these steps and actually the energy that transpires, okay? So we already said we have a couple of first steps here. We got to make some ions. So in step 1, sodium must lose an electron. So what we have to do in order to actually remove the electron from sodium, it requires energy to be put in. That energy is going to be equal to the first ionization energy of sodium. So if you would look at a table or something to look it up, you would see that's 496 kilojoules per mole. So in fact, that's energy we have to put into the system. For the chlorine, to gain the electron, adding the electron will release energy. So that's actually a pretty favorable thing, because we would then be releasing energy, which puts the chlorine at a lower energy state. That will release 349 kilojoules per mole of energy, and that's a negative value, releasing the energy out. So if you take those two numbers, notice that more energy is required than is released, because the sodium requires 496 joules put into it, and the chlorine will only release 349, which means that we're actually increasing the energy by 147 kilojoules per mole. And that doesn't seem to be in the right direction. As I said, chemistry works on stability and lower energy levels. And in fact, we've just increased the energy. So something's weird? No, we're just not done yet. So hold that thought. Recall, the goal is lower energy. That's a problem. So right now, ion formation is actually an unfavorable process, especially forming positive ions. It's an unfavorable process generally. It requires more energy than it actually releases. So again, this can't be the end of the story, because if it was, then I'd be a liar. I don't try to be a liar. So why form ions? Well, because the end result is way better. So even though we've had to put a little bit of energy in, we still have the ability to go one step further. So step 3 is going to be the attraction of the positive and the negative ions that we've just created. And then we will also move on to step 4, which is actually going to put the individual sodium chloride compounds in a big block, like think a big solid block of salt, and that will be the last step. So in step 3, we will attract the ions to each other, and notice the number here. We will release 493 kilojoules per mole. Do you notice the negative is signaling release of energy, whereas on the previous slide, when you put energy in, that's a positive value. So kind of keep that in mind. That'll be something coming up in a couple chapters. So we attract the two together, and we do actually release 493 kilojoules per mole of energy. So if I take the previous number from the last slide, 147 was our net energy required at that point. Now we've released another 493, which brings our total now to a lower energy value. So we've now released 346 kilojoules per mole and brought our sodium and chlorine to a lower energy level, and that's pretty great. That was the point. So it is, in fact, at this point, lower net energy from start to finish. That's great. But again, we're not done yet, because if we put all of these individual NaCl's together as a big solid, we will actually create less energy. And I'm sorry about the repetition of the word unit. Each formula unit has less kinetic energy. So if I put together all of these formula units of NaCl, I'm going to lose an additional 293 kilojoules per mole. And so if I add that on, if I take and put it into a solid form, I'm actually going to release even more energy, and that would equate to 639 kilojoules. You do not have to memorize any of these values. Simply what I'm doing is trying to show you that formation of ions is not a favorable process. But when those ions attract to each other, as step 3 shows, you do end up with a lower net energy. If you then imagine step 3 is, say, sodium chloride kind of in a molten form, like it's a liquid type of a form. Once I pull those together as a solid, I create even more energy release, which is an even more stable type of a thing. So again, because you see this very negative value, 690 or 639, what that means is that the sodium chloride itself is a very stable solid. And I think you know that. Sodium chloride is sitting on your kitchen tables, probably at home, and it's not degrading or, forming noxious chlorine gas that you breathe in and then, like are afraid to die at home or something. So yeah, it's very stable, and it's very stable because the chemistry is as it is. So a little information about that. To also give you just a little bit more information, this graph will also show similarly what we just talked about. So it's kind of crazy and all over the place, but if you kind of follow it, here would be the starting point. So 1 mole of sodium and 1 mole of chlorine, and these are the atoms, and you can see 147 kilojoules is actually required to form the ions. Then when we pair the ions, you can see here 493, and then if we form the solid plus the 293, so that gives us the overall of 639 kilojoules. So you can kind of see a graphical form of how the energy again goes up and down. So again, this is where we started, and we had to put in energy, then we could drop the energy, and then if we formed a full solid, we could drop the energy even more. So kind of just a graphical form, which is sort of cool. Okay, so next, in looking at forming ionic bonds, we'll take a closer look at electron configurations, because the electron configurations also explain why certain things form certain ionic bonds. So you can see what I have on the screen right now is the electron configuration. It's the noble gas configuration, or I'm sorry, noble gas core. configuration for sodium and chlorine. And what I would have you note is the valence. So sodium is a 3s1 and chlorine is a 3p5. So you can see their valence electrons there. Excuse me. And what's going to happen, as we know, is that the transfer of the electron is going to happen from the sodium to the chlorine. So it would then up the 3p5 to a 3p6, and then 6 plus the 2 from the s orbital for chlorine will lead to 8. So sodium will transfer its valence electron. It'll achieve its noble gas configuration. And so the ending configurations would look like this for the ions. One little special word to throw in at this point is the word isoelectronic, an important word to understand the meaning of. Having the same electron configuration as something else. So for instance, as you can see here, the sodium ion is isoelectronic with the neon atom because they have the same electron configurations. Similarly, the chloride ion is isoelectronic with argon. So that's a typical multiple choice question that you could see, is asking about isoelectronic and which things are isoelectronic. So a good little definition to have in your back pocket. Ionic bonding basics. So we understand that atoms will form ions because they want to achieve a different electron configuration. Generally, they're looking to achieve a noble gas configuration, but achieving what's called a pseudo-noble gas configuration is also relatively stable. Basically what it is it is a completely full subshell. So you could have a full S with nothing in the P. And additionally, sometimes a pseudo-noble gas configuration can even be those half-full configurations that we've actually talked about with ionization energy. For instance, nitrogen, relatively stable because it has this sort of pseudo-stable kind of configuration. So we can determine how readily an atom will form an ionic bond based on its ionization energy. So again, you can see a lot of things really, coming together here as we've been talking here for just, a few different lessons so far. The fewer electrons an atom needs to lose, the more readily electrons can be lost, meaning it requires less energy to remove the electron. So for instance, if you take a look at like lithium or sodium, they really want to form ionic bonds because they really want to lose those electrons. So they have a low ionization energy, which means that they really, really, really like to form ions. And then after that, they can form the bond. So 1A elements are more easily ionized than 2A and 3A. Whoops, sorry. Which again means that 1A elements are more likely to form ionic bonds. So to continue, if you move from left to right across the period, it's going to be harder and harder to ionize the atom. And again, when we use that word ionize, it doesn't literally mean to form an ion. It actually literally means to form a positive ion. So as you move from left to right, you get over towards like chlorines and fluorines, they don't ionize very easily because they don't want to lose any electrons. So understand that word has kind of a specific issue with it about positives. Go down a group, it becomes easier to ionize. Hopefully you remember that the reason for that is because of shielding. Down a group, more energy levels that allow the electrons to sort of pull out from the protons in the nucleus, and they're just not as easily impacted. So again, if you go down a group, it's easier to ionize, easier to form a positive ion because they're just not holding on to the valence electrons that much. And again, this matches ionization energy trends. It's all the same reasons, shielding. Most elements, this is kind of an interesting little thing. Most elements in 3A do not form compounds with 3+ ions. And so again, I'm talking about aluminum, for instance. Aluminum is just something that we like to talk about how it forms a 3+ ion, but it's not something that happens very often. And that's because to remove 3 electrons is just a little tricky. And we actually talked about this similarly with nitrogen. Nitrogen needs to gain 3 electrons to become like neon, and that's tricky. That's really hard. It's right on that threshold. It can happen, sure, but does it happen all the time? Not really. So in fact, we tend to form more covalent bonds with those chemicals just because it's easier. Again, chemistry is based on stability. And if it's a hard process, if it's something that's going to require me to go round up a whole bunch of extra electrons, that's probably not going to happen. It's going to happen in an easier way. So chemistry is kind of cool. It's sort of like path of least resistance. It does things in the easiest possible way. So yeah, I think most humans can relate to that. So at times, we can form ionic compounds with those groups, like we just talked about. But again, it's just not something that's typically something that happens. Just to give you an example, thallium will sometimes form +1 and +3 ions. And in fact, I'd like to talk about that. Look for thallium on your periodic table. Thallium is element 81. It's at the very bottom of group 3A. My questions for you is going to be, why will thallium form +1 or +3 ions? It's kind of important to be able to think about an electron configuration in terms of why behavior of something happens. So on the screen I have for you the electron configuration of thallium. So you can see it's a xenon core, 6s2, 4f14, 5d10, and sp1. So my thought is you can probably figure out why the +1 would happen. So what's your thought? Say it out loud. Be brave. That's right. I'm so glad. Yeah, if you're going to form, actually, look at that. I did the 3+ first. Oh, well. If you're going to form the 3+, sorry, I'm kind of doing the hard one backwards. Let me go down here. So let's look at the second one first, sorry. In order to form the +1, all we're going to lose is sp1, or I'm sorry, 6p1. And notice we now have the 2 electrons left in 6s2. So that would actually create a pseudo-noble gas configuration, and it would allow us to be relatively stable as thallium +1. Whereas thallium +3, you'll notice that you lose actually all of the 6s. So you lose the 6s2 and the 6p1, which is a loss of 3 electrons, which of course corresponds to the third or 3+ charge. So that would be also what you would consider a pseudo-noble gas configuration, mostly because you still have electrons left in the 5 and still electrons left in the 4, and so it's technically sort of a funky little thing. But yeah, 3+, 1+, basically the electron configuration matches the behavior and the formation of ions. So hopefully that makes some sense. If you continue down the periodic table, so we've talked a little bit about group 1A and 3A, 5A a little bit. If we take a second and talk about group 4A, we talked about this a couple times. They do not form ionic compounds hardly at all, and that's because of that whole gain 4, lose 4. It's all kind of hard. Tin and lead often form 2+ ions, but it is also possible for them to form 4+ ions, which I've said before. So to answer a question of why, if you notice the 2 electron configurations here for tin and lead of the 2+, recognize that what they're losing is actually their p electrons in both cases. So tin loses the 5p electrons, and lead loses the 6p electrons. Well, answer this next question then. If they can form a +4, where do the other 2 electrons come from? How about right here? And how about right here? So if it loses the rest of that energy level, just like we were talking about with the thallium, then it can also form a +4. To look at group 6A and 7A, very high electron affinities, again, high electronegativities. They gain electrons readily. They form very stable monatomic ions. So again, 6A would be like O2 negative, or 7A something like F negative. So those are very, very stable. Excuse me. With other groups, you can also notice that we can form polyatomic ions, things that you've heard of before, like for instance, sulfate or phosphate. So we can actually covalently bond, say, sulfurs and oxygens together with covalent bonds, but then we form an overall ionic charge on the whole thing. So again, it fits in with the ionic idea, even though it has covalent bonds holding the structure together, it would then ionically bond with something additional. Transition metals, which we certainly would have talked about a lot in general chemistry, have several different ions that they could form, and it's all based on just variations of their electron configuration. So you can see here with iron, iron tends to form a +2 charge a lot of times, and that is by losing its 2 4s electrons. But it can also form a 3+ ion, and it does that by emptying out the 4 and then additionally losing one of these d electrons, which again, it's going from a 3d6 and it goes down to a 3d5. Well, how many does d fill with? It fills with 10. So for an iron to go from a 3d6 to a 3d5 actually makes a pretty good amount of sense because it's going to a half full orbital. And that's a relatively stable configuration. So again, the two different ions make sense for the electron configuration, and in fact, you're going to see that throughout. So hopefully I just answered the question, why is this okay? Other common ions, sorry about the spacing on this one, transition metals also form other common ions. The ones that are in yellow are the ones that you definitely should be kind of familiar with. Cobalt, nickel, and copper, also manganese tend to form +2s. The zinc, which is a 2+ all the time, and your silver, which is a 2+ or a 1+, excuse me, all the time. You need to know those definitely. My final question for you would be, do you remember or could you explain why the ones in yellow make sense? And it's all going to be based on the same types of things that we were just talking about. Excuse the bell. So the same types of things we were talking about. So you look at their electron configuration and you recognize which electrons it might be losing.
Attention staff,
Oh,
we do have some more
geez.
packing tape in the office.
Oh, good. We have
There
packing
is some more
tape.
packing tape in the office.
Good. I'll be sure to go get some later. All right. So hopefully you can look at electron configurations and kind of figure that out. Again, bring your questions to
Will
class.
the following students
Oh,
please
geez.
report to the office? Mariah Deemer, Lucas Leonard, Anna Ryman, Dylan Zachary,
Yeah.
Stone Bowles,
Yeah.
Hannah Dickus, Donovan Franz,
It's a lot of people.
Kendra Michaelis,
Uh-huh.
Jared Olds,
Cool.
and Caleb Weisman. Thank you.
Okay, cool. All right. So,
The
fine.
following students please report to guidance. Derek Belcher, Jaden Buka, Paige Damon, Kirsten Bressler, Mia Conklin, Joe France. Please report to the office. I'm sorry, please report to guidance.
Okay, hopefully they're done now. So quickly, recalling trends in ionic size. Hopefully you can kind of just see in this picture something that we've talked about before. You can see that, rubidium as a positive ion is relatively smaller than pretty much everything you see over here. So in, again, a lot of cases, your negatives tend to be larger than your positives, and you can also see some of these positives that have really lost a lot of electrons, how absolutely tiny they actually become. So just a little graphic to hopefully tie back into ionic size again, since we're talking about ions today. So all right, I'm done. Hopefully no more crazy announcements. So wow, awesome. Just have a great day. See you later.